Hi everyone, thanks for coming. The title of my talk is Fooling Gaussian PTFs via Local Hyperconcentration. This is joint work with Ryan O'Donnell at CMU and Rocco Servideo at Columbia. In this talk, we'll be concerned with a basic class of functions, the class of polynomial threshold functions, or PTFs, over Rn. These are functions mapping Rn to plus minus 1, and they have the form sine of p, where p is a polynomial. To give an example, we have here a quadratic polynomial p corresponding to an ellipsoid, and f is simply the function that takes value 1 on all points within the ellipsoid and minus 1 on all points outside the ellipsoid. And even though I've given you an example of a function that lives in R3 here, in this talk, please think of the ambient dimension n as tending to infinity. So PTFs for us will be a very natural way to represent high-dimensional geometric objects. And PTFs are extremely well studied, both within theoretical computer science and also beyond. There are many ways to measure the complexity of a PTF, and in this talk, we'll focus on just one of them, a natural one, the degree of the polynomial p, which we'll denote as d throughout this talk. So on the left here, we see the d equals 1 case, which captures exactly the class of all half spaces. With d equals 2, we include objects like ellipsoids. And here, we already see that with d equals 5 and 6, we're dealing with some pretty complicated looking polynomials. And in fact, in this talk, please do not think of d as a constant, but rather as growing with ambient dimension n. For concreteness, we can think of d, the degree of the polynomial, as being, say, logarithmic in n, where n is again the dimension of the ambient space. There are many questions we can ask about PTFs, and in this talk, we'll focus on just one of them, that of constructing discrepancy sets for PTFs over Gaussian space. So let me try to say what the problem is. Consider Rn, our ambient space, endowed with the Gaussian measure. We want a small set of points, the smaller the better, with the following property. For every degree d PTF f, if f's Gaussian volume is delta, I'd like it to be the case that roughly a delta fraction of the points fall within f. So this is a small set of points that approximates the Gaussian volume of every degree d PTF. If we think about it for a few minutes, it's not too hard to see that a random small set of points works great. So this is really a problem in explicit constructions. It's really a problem in pseudorandomness. So let me actually try to restate the problem in an equivalent way in the language of pseudorandom generators, or PRGs, over Gaussian space. PRGs are more well studied over Boolean space, but they are also very natural over Gaussian space. So let me give you the definition of a PRG over Gaussian space. An epsilon PRG for class C is an explicit function g mapping r bits to Rn with the following property. For every function f in the class C, the expectation of f under the Gaussian measure, the Gaussian volume of f, is well approximated up to an epsilon additive factor by the expectation of f under the output of the function g. So we can consider the problem of constructing PRGs for all sorts of function classes. In this work, we'll focus on degree d PTFs. And to draw the connection between PRGs and discrepancy sets, we note that the image of a PRG is exactly a discrepancy set. So if R denotes the C length of the PRG, R and the size of the discrepancy set are exactly related up to an exponential factor. So the problem of constructing a small discrepancy set is exactly equivalent to the problem of constructing a PRG with short C length. So with this definition and with this equivalence, I can now state our main result, which is a new PRG for PTFs over Gaussian space. We give an epsilon PRG for degree d PTFs over Rn with C length d over epsilon to the log d times log n. This question has been quite well studied, and previous best C lengths all had at least an exponential in d dependence on the degree. So the main contribution of our work is to bring this exponential dependence down to a quasi-polynomial dependence. We still have quite a lot of work to do though. The probabilistic method shows that there exists PRGs with linear in D seed length. So it'd be extremely interesting to further improve our dependence on D down to polynomial in D, and hopefully one day to linear in D. I should also mention that a Gaussian space version of the problem that we study is in fact a special case of the Boolean space version, the problem of constructing PRGs for degree D PTFs over Boolean space. The fact that Gaussian space is a special case of Boolean space is a consequence of the central limit theorem, or in this case, the invariance principle. And for the more challenging setting of Boolean space, the current best Boolean seed length is still exponential in D. We are hopeful that our techniques and our work will lead to progress on this more challenging setting. But for now, our results only hold for the easier Gaussian space setting. As I mentioned, there's been quite a lot of work on this problem, both over Gaussian space and also the more challenging Boolean space. It's a little hard to eyeball these seed lengths, especially in a short amount of time. But let me bring your attention to the third column here, which denotes the allowable and non-trivial range of degrees given by previous work and our work. As you can see, many of the previous results hold for degrees that are constant or slightly superconstant. I would like to point out the work of Mecker and Zuckerman, who gave PRG both over Gaussian space and also the more challenging Boolean space, which held for degrees all the way up to log n over log n. There's also the work of Kane, which gave a Gaussian PRG that works for degree all the way up to log n. So the main contribution of our work is a PRG over Gaussian space that works for PTFs of degree super logarithmic in n. Our result holds all the way to degree 2 to the square root log n. So having stated our result, here's the structure for the rest of this talk. This paper was fairly technical and lengthy. I thought I would abstract from the paper one of the key technical ingredients that I hope is of independent interest. It's a new structural lemma about polynomials. And in the rest of this talk, I thought I'll tell you about this lemma and also sketch the proof of this lemma. The lemma, roughly speaking, says that an arbitrary polynomial, when hit by a random restriction, collapses to a simple polynomial with many enjoyable properties. So in the rest of this talk, I'd like to state this lemma more precisely. I'd like to tell you about what a random restriction is over Gaussian space. And I'll also like to tell you about what these enjoyable properties are. Before moving on, I just want to mention that with this lemma, there's still a lot of technical work to use this lemma to get the PRG. And in fact, this work constitutes the bulk of our project and paper, but due to time constraints, I will not have time to tell you about the work that's involved in using this lemma to get a PRG. I'll focus just on the statement of the lemma and a sketch of the proof of this lemma, which, as I said, I hope is of independent interest and I hope you enjoy hearing about. To state the lemma more precisely, I have to tell you about a special subclass of polynomials, the subclass of concentrated polynomials. These polynomials have a very simple definition. We say that P is concentrated if the variance of P is a tiny fraction of its expectation. This is intuitively a very appealing property in that such a polynomial P we can think of as being morally constant, or equivalently morally degree 0. So even though syntactically P is a degree D polynomial, for all intents and purposes, it behaves as if it were a constant function or degree 0 polynomial. And one way in which this condition implies that it's morally degree 0 is that for most x's, for most inputs x, P of x takes the same sign as the expectation of P of x. So that's the definition of a concentrated degree D polynomial. It's one which is morally degree 0. Of course, not all polynomials are concentrated. And our lemma concerns the relationship between a non-concentrated degree D polynomial and a concentrated degree D polynomial. So here's our new structural lemma. Consider any degree D polynomial P, denoted here by the red dot, which may not be concentrated. And in this case, it is not concentrated. Our lemma says that if P is hit by a mild random restriction, P becomes concentrated with high probability. So that's our lemma in pictures. Here's our lemma in words. An arbitrary degree D polynomial, when hit with a mild random restriction, becomes concentrated. It falls into this green circle with high probability. So in the next few slides, I'd like to tell you about what a mild random restriction is, and also sketch the proof of this lemma. But before moving on, I should mention that we in fact show something stronger, which is that P becomes not just concentrated, but hyperconcentrated, where hyperconcentrated polynomials are a further subclass of concentrated polynomials. The definition of a hyperconcentrated polynomial is slightly technical, and I will not give it in this talk. Roughly speaking, it says that the hypervariance of P is a small fraction of its expectation, where hypervariance is a quantity that can be exponentially larger than the variance of P. So this is an exponentially stronger condition than concentration. However, for the rest of this talk, it's fine to conflate hypervariance and hyperconcentration with variance and concentration. Okay, I'd like to tell you about the notion of random restrictions over Gaussian space. This is another notion that is more well studied over Boolean space, but it's also very natural over Gaussian space. So here's the definition of a random restriction over Gaussian space. Let P be a polynomial. A lambda random restriction of P is the polynomial Q. It's a random polynomial. Q of x is P of root lambda x plus root of 1 minus lambda y, where y is drawn from a Gaussian. So we think of P as living over Gaussian space. It is sort of expecting a standard Gaussian, and here we have fed it most of a Gaussian with variance 1 minus lambda. So that is what it means to take a random restriction of a polynomial P over Gaussian space. And I just want to make a couple of observations and remarks about this definition. One is that the smaller lambda is, the harsher the random restriction is. We can think of lambda as corresponding to the star probability in a Boolean random restriction. It's the analog of a star probability in a Boolean random restriction. And here indeed, the smaller lambda is, the more of y we are feeding into P, and hence intuitively, indeed, the harsher the random restriction is. Another way to view this definition is that Q represents P's behavior in a local neighborhood around this random point y, where lambda is the radius of this neighborhood. The smaller lambda is, the smaller the neighborhood is. The larger lambda is, the larger the neighborhood is. With this definition of random restrictions, I can now state our structural lemma slightly more precisely. We show that any degree D polynomial P, which may not be concentrated or hyperconcentrated, if such a polynomial P is hit by a lambda random restriction, where lambda is 1 over quasi-polynomial in D, it does become hyperconcentrated with high probability. So that's the statement of our structural lemma. And keeping in mind this view of random restrictions from the previous slide, it can be viewed as saying that for most points y, if we zoom in on P's behavior around y, P behaves like a constant function in a fairly large neighborhood of radius 1 over quasi-polynomial in D around this random point y. And for this reason, we call our new structural lemma a local hyperconcentration theorem, that P at most points behaves locally around that point as if it were a constant function. So that's our lemma. Let me tell you about how we prove this structural lemma. Again, our structural lemma, our local hyperconcentration theorem, says that any polynomial, any degree D polynomial P under a random restriction becomes hyperconcentrated or morally constant or morally degree 0 with high probability. So how do we prove such a statement? We proceed as follows. We first show that under a random restriction, it becomes morally degree D over 2. And then after further random restriction, it becomes morally degree d over 4. And after another random restriction, it becomes morally degree d over 8, and so on and so forth. And after log d iterations of random restrictions, it finally becomes morally degree 0, or in other words, hyperconcentrated. So if we compose all log d iterations of this random restriction, we get our local hyperconcentration theorem. This idea of composing smaller random restrictions into a global random restriction is due to Avi, and we have to thank him for this really simple and elegant idea. And with Avi's great idea, it's not too hard to execute the proof. The technical ingredients are Hermite analysis, and also the Cabré-Wright anti-concentration inequality for polynomials over Gaussian space. So that's the statement of our local hyperconcentration theorem and the proof of it at a very, very high level. And this essentially concludes my talk. I just want to outline two open problems that are related to the local hyperconcentration theorem that we proved. We showed that any polynomial p, when hit by a lambda random restriction, where lambda is 1 over quasi-poly in D, becomes hyperconcentrated with high probability. We in fact conjecture that lambda being 1 over poly D suffices, so this an even larger neighborhood and even milder random restriction suffices to bring p to become hyperconcentrated with high probability. If this conjecture is proved, using the framework that we set up in the rest of the paper, it would immediately imply a PRG for PTFs over Gaussian space with C-length poly in D improving on our current quasi-poly in D. So that's open problem number 1. The second open problem is to prove an analog of our local hyperconcentration theorem for polynomials over the more challenging Boolean space. We conjecture also that such a random restriction lemma should be true. If this lemma is proved, it wouldn't directly give a PRG over Boolean space, but it will be a very promising and interesting first step towards it. And that concludes my talk. Thank you very much for listening.